say like directly above the head.
Just tell it.
Yeah.
Uh, sorry, Prathamesh, did you say perpendicular to the?
Given line
Observer.
of longitude.
Okay. Okay. So anyway, interesting.
Right.
Huh. Okay. Yeah. So we got a lot of definitions here. I think Angel's answer comes basically closest to what we were looking for, right? So basically, when you say highest point during the day, you're basically talking about a local meridian pass. It means that the sun has touched your local meridian. All right. You need to picture this huge grid full of longitudes, right? And one particular longitude from the North Pole, connecting the North Pole, South Pole, and your zenith is your local meridian. Okay. So let's say for every degree we define a longitude, right? Like we have 360 longitudes on this celestial sphere. Then the one passing directly above your head is your local meridian. So when the sun intersects this local meridian, that is when you know it is noon. Now it can intersect your local meridian either at the zenith or not. And in fact, it very, very rarely is at the zenith. It's at the zenith like once a year or twice a year. All right. At some places, it is never at the zenith. Those of you who did your homework on zero shadow day, you will know that only places within the Tropic of Cancer and the Tropic of Capricorn, that is plus 23.5 and minus 23.5 degrees, only locations there can have a zero shadow day. Right?
Yeah, I tried to like calculate mine, and there is no day like that.
Okay. Where do you live,
Yeah,
Angel? Nepal, right? You're from Nepal.
Yeah.
Okay.
Yes.
What is the latitude of Nepal? What are we talking about?
I am in Butol, and in this city it's 27, I guess. So it is
27. Correct.
Yes.
So April has no zero shadow day where she lives, right? So Aditya, who just joined, he lives, I think, in Kerala. So he is probably less than 13 degrees latitude. So he will definitely have a zero shadow day. So good job, Angel. I think at least you went back and checked out. So those of you, for everyone here, even the new joinees, right? It's a fun thing to just look up on which day of the year is zero shadow day for you. And on that particular day, if you have a zero shadow day, there will be no shadows cast anywhere. It actually looks pretty creepy because suddenly it looks like there's this loss of dimensionality in all the objects you look at. There is no shadow, right? So it's pretty cool. So on most days, though, that is just one day of the year, right? On most days, there is always a shadow cast. Why? Because the sun is not at the zenith. Think about it. If the sun was directly above your head, of course, there's no shadow cast, right? The only reason you always have a shadow is because the sun is a bit off. It's offset from the zenith. Therefore, noon can also be defined as the time of the day when the shadow cast is the shortest. Do you guys agree with me? So if I have like a full range of shadow lengths throughout the day, the time of the day when you have the shortest shadows is going to be the noon, right? Because of the meridian pass. Okay, I'm sure all of you got it by now. So yeah, that was just for some warm up. I've already asked you guys this before. Sunset is defined when the sun is just near the horizon, right? Usually approximately 6 p.m. And again, sunrise is just when it's at the horizon, that is 6 a.m., right? And this is again important for visualizing the phases of the moon. And you should be very familiar right now with visualizing the Earth and the sun. But I think there should be some more clarity in understanding orbital parameters, because right now we use phrases very conveniently and easily, right? We say orbital tilt, then we say orbital inclination, we say whatever, altitude, latitude, and a certain tilt and inclination. These things are actually different, and they have very precise meanings in astronomy. So let's take a look at that. Let me present. Okay, you shall be able to see my screen now. So I think this was a fairly informative website. So let's use this. It's called astronomy.swin.edu. It's by Swinburne University, is what I'm guessing. So let's go over orbital elements today. So if you guys can close your eyes and think about an orbit, right? And for those of you who I shared the video with, you guys already know how complex this really is, right? It's not as simple as you think. It's not even as simple as saying, okay, this is the ellipse I'm drawing around the sun, and that's all there is to it. No, right? The ellipse is dynamic. The ellipse is moving. The ellipse's position is actually moving across thousands of years. The Earth is precessing. The Earth's tilt is also changing. There's a lot going on. On top of that, the solar system is moving around the galactic center, right? So this is at something like 260 kilometers per second. So the Earth is actually not even spinning in an elliptical orbit. It actually has a spiral orbit, right? It's like spiraling across space as the solar system is moving, and it's moving incredibly fast. So you are really never at the same place on what is today's date. On the 10th of June next year, you really are not in the same place that you started. Interestingly, there was a meme I shared with you guys, and the homework was to explain the meme. For those of you who are not there, let me try to screen share. Yeah. Okay. Meanwhile, can anyone tell me what the meme was about and what it had? Anybody who remember it? Where did the meme go? Vishal, did you see the meme?
Yeah, it was about somebody says he turned 23 years on that day, and someone asks which one, is sidereal or solar or Earth days, and he says yes.
Okay, so what does that mean? Why does he ask, is it solar, blah, 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 blah. So you should be able to see this now. So this is the meme.
Tropical. Yeah, not solar. Oh, that's sure.
Right. So I turned 24 tomorrow. And she says, is that sidereal, tropical, or anomalistic years? Right? And he doesn't know what to say. So what does this mean? And what does she mean by sidereal, tropical, or anomalistic years? And why are they different? So can someone start with sidereal? What do you guys think sidereal means?
It's a time that passes when we are in space.
Correct. So sidereal has a root, and the root of the word basically means with respect to the stars. All right. So sidereal is talking about sort of with respect to a permanent framework. You guys need to realize that if you look at a particular day, 24 hours orbit, you think you're coming back to the same place in exactly 24 hours, but you're not, because the Earth has moved in its orbit around the sun, right? So it's not constant. The reference is not constant. So a sidereal reference frame means with respect to the distant stars. And of course, because the stars are so far away, for us, we can assume that the stars are pretty much constant wherever they are, right? So because of the permanence in their places, we can use this sidereal reference frame. So that is your first year that you can define. And I'm going to Google it as well, because it's nice to know the numbers. The second one is tropical. Now, can someone guess what tropical could mean?
It's another name for solar year.
Okay, what is solar year?
One complete revolution.
Okay, but we're really talking about like time here, right? Like when I say sidereal day or a tropical day, I'm talking about different time durations. So
Yeah.
why is a tropical day different?
A sidereal year means time taken from an equinox to another equinox, something
Okay.
like that. Yeah.
So that's a good enough. Actually, you are wrong. That is actually tropical. That's the definition for tropical. So let's go over the definition for sidereal. The sidereal year is the time taken for the Earth to complete one revolution of its orbit, as measured against a fixed frame of reference, such as fixed stars. Okay. So Latin for sidera, singular sidus. So that's what it means. It means stars. So this duration, interestingly, is 365.25 something. right? And here it's 365.24 something. Here again, it's 365.259. This is 256. So these seem really small, and you must be thinking, what? It shouldn't matter. It's so small. But if you look at history and over time, how Aditya, can you mute yourself? There's a bit of noise. So if you see history and how time references have changed over thousands of years, you'll see that these very small factors add up, and they add up into huge amounts of time. You should really watch that Veritasm video called How the Sun Moves, and it really brings into attention how much difference it can make over, say, 1,000 years, over a millennium, right? So these are different. So this is the sidereal year. Someone is here. Okay. Whoa, Jishnu is here. All right. Okay, so then we were speaking about the tropical year, and that is the period of time for the ecliptic longitude of the sun to increase by. Okay, so this is more with respect to the, now you're talking about the solar system and not the distant stars. So anyway, before I move forward, I just want to introduce you all to Jishnu. Hi, Jishnu. There are a couple of new people here today. I think 4 to 5 new people. So can you say something? So that we can. Yeah,
I didn't
you're
hear
audible.
anything.
Yeah, you're audible.
Okay, so
No.
I had my headset disconnected while you talked for like 2 seconds, so I
Okay. Yeah, no, I just wanted you. I just wanted to introduce you to a couple of new people here. So there is Prathamesh, there is Smriti, there is Joydeep. So quite a few new people today. And
yes, I just dropped in to say hi. I'm still at my office, so I'm about to leave. So I saw your link and I just joined.
Okay. All right. So yeah, I think if you're free sometime this week, just know we can have a 1-hour session. You just let us know.
Yeah.
Cool. So we are just doing orbital elements today for planetary orbits.
Okay.
And cool. Yeah. All right. See you in the next class.
Sure.
So the tropical year. Yeah. So coming to the tropical year. Is a period of time for the ecliptic longitude of the sun to increase by 360 degrees. Okay, ecliptic longitude. Okay, let's not go to that definition. Let's stick to the definition of the equinox. So basically, we are measuring tropical year with respect to the equinox. The tropical year comprises a complete cycle of seasons, right? So tropical, the word itself tells you we are talking now in reference frame of the equinox. So the most important concept to understand is, if you think about a 360-degree rotation of the Earth, and if it completes that, it still has some amount left for it to reach the same position with respect to the sun. So it would actually be easier if I could draw it for you. I'll try it at the end, so I don't want to, in case my laptop hangs. But hopefully you can imagine that when the Earth sweeps 360 degrees, with respect to the distant stars, yes, a day is completed, right? But with respect to the sun, the Earth has moved just a teeny bit. And because of that, it has to cover some extra amount of angular distance to be in the same position with respect to the sun. So that extra time constantly changes throughout the year. And a solar day is defined as the sidereal day plus this extra time, right? So this extra time constitutes the tropical day or a tropical year, right? So this is with respect to the sun, essentially. Anomalistic year is a time taken for the Earth to complete one revolution with respect to Apsidus. The orbit of the Earth is elliptical, so we won't go over here because I think it will be better if we now switch to the orbital elements and come back to this later. Okay. We all remember Kepler's laws. First one. You can.
Okay.
So it's basically 2 extreme points. So you're talking about a focal point over here, and points across the semi-major axis. That would be the Apsidus.
Okay.
So yeah, we will encounter this again in orbital elements. So yeah, let's quickly go over Kepler's laws. We all remember that anyway. All planets move along elliptical orbits. with sun at one of the foci. Second law, a line connecting a planet and the sun sweeps out equal areas in equal intervals of time. This is an important derivation as well, right? When you derive it from Newton's laws. And finally, the square of a planet's orbital time period, t square, is proportional to cube of a, semi-major axis a, right? So t square is proportional to a cube. We remember that. Now, you should understand that when you think of an ellipse, right, everything you need to know about the ellipse is defined just by these two guys: semi-major axis, orbital eccentricity. If you know these two guys, you pretty much know everything about the ellipse. And if you imagine it, you actually don't need anything else. Why? Because eccentricity is defining how squished the ellipse is, or like, you know, how elongated the ellipse is. And semi-major axis is telling you this distance from the focus, right? Okay, we don't have a picture of the ellipse here, but anyway, so you get the point. So if you just have these two information points, you know everything about the ellipse, right? So I'm going to skip orbital eccentricity. Maybe we'll just take a look at it quickly. I think you guys remember this formula, but essentially you're talking about how squished it is. So if it is not squished at all and it's a circle, you've got an eccentricity of 0. And on the other hand, you've got a eccentricity of something like 0.95, close to 1 over here, right? At 1, it would be, I'm thinking, a plane or a straight line. This is the formula, but you're going to have to understand theta, which is anomaly, true anomaly. So we'll come back here. All right. So now that you understand semi-major axis, orbital eccentricity, you already know perihelion distance. Perihelion distance is for the object the closest approach to the focus, right? So the closest or the shortest point distance to the focus. So now we get to the interesting parts. The first 3 parameters tell us information about the shape of an orbit. Is that clear? Like, I mean, it tells you how the ellipse looks and so on, right? It's the shape of the orbit. Okay, just noise here. Eccentricity, okay. Yeah,
Like if you scroll down a bit, you can slide the slider so it shows you.
Oh, nice.
Yeah.
So.
At one, it's a parabola.
Oh, really? Okay.
Yeah.
At 1, it's a parabola. It opens up. Right. So I think if you have very high eccentricity orbits for like asteroids and stuff, so usually it would turn into a parabola sometimes, right?
Yeah, hyperbola.
For extremely hyperbola.
Yes.
Okay. Cool. So you guys can try this. It's in the link is there. Yeah. So yeah, so these 3 help in kind of defining the shape of the ellipse. So the next 3 require you to kind of visualize it properly. Like, you need to be able to imagine it. So just make sure you have the picture in your head. So first one is orbital inclination. So orbital inclination needs a reference plane. So in the solar system, we usually take the Earth-Sun plane as the reference frame. So although all the planets and asteroids follow the elliptical orbits around the sun, these orbits do not lie on the same plane. Like, we know, for example, that Mars, Jupiter, Mercury, they're all on different planes with respect to the Earth-Sun plane. So this tilt is nothing but the orbital inclination, right? So if you take the entire plane of, say, Mercury and you compare it with the Earth-Sun plane, that tilt you get is nothing but the orbital inclination. So we have adopted the plane in which the Earth moves around the sun as our reference plane. And with this convention, the Earth has an orbital inclination of 0 degrees. So you get it. So Mars is 1.85, Mercury is 7 degrees, and Pluto's is a very high 17.15 degrees orbital inclination. So don't confuse this with like obliquity, which is mentioned here. So the tilt of the planet's axis. So when we speak about orbital inclination, we are speaking about the entire orbital plane. And we're not talking about like the axis tilt of the particular planet, right? And actually the axis tilt is pretty complex in itself. The axis tilt is also changing with time. It doesn't remain constant. So I think I'll find some other source for that. Right now we know it to be 23.5 degrees, right? And that itself is, of course, the axis is precessing. But along with precessing, the amount by which it is tilted is also changing. So we'll come to that. And then there is ascending node. So I hope orbital inclination is clear and we have the symbol I for it. Usually we call it the 6 orbital parameters, 6 parameters that are the most important for defining any orbit. So what is ascending node? So now if you can again visualize these in 3 dimensions, you're talking about the reference plane of the Earth-Sun system. Then you're talking about the second plane of, say, Mercury intersecting in space, right? So when they intersect, there is a particular point at which the 2 ellipses meet. But there are 2 points like that, right? There's not one, there are 2 points like that. So one of them is called the ascending node. So how do we distinguish it? So that's basically, it depends on the direction. So let's read this. So for objects orbiting the sun, the most convenient reference frame is again the Earth. And you're talking about is usually quoted as the angular position at which a celestial body passes from the southern side of a reference plane to the northern side. So this is how you distinguish between the 2 points, right? In the other point, the object is going from the northern side to the southern side. So that's how you would distinguish. And if you guys remember vernal equinox, like how are we distinguishing between the autumnal equinox and the vernal equinox? So it's kind of like this approach of southern to northern is what is the convention we take. So this is the first row is the top view. If you look at just the first 3 pictures, so this is basically omega, right? But this is represented by ascending node is this omega. Wait, is this? Yeah, unfortunately, both of them are omega. So you'll have to distinguish it by the symbol. But this is basically the top view. And this is the ascending node, as you can see. So if this is the y-axis and this is the z-axis, at some particular point, it is intersecting the Earth-Sun orbit. But of course, you need to understand that if you're looking at another solar system, you have to choose a reference plane, right? So how do you choose a reference plane? So usually you would think of, okay, which planet is the most visible planet? And then that planet's orbital plane would become your reference. That is in the case of looking at other solar systems.
Why can't we choose always sun?
Sun as the reference point?
Yeah.
Sun is the reference point, but the sun is the point, right? So we need a plane of reference. So when we are talking about the reference plane, we are talking about this 2-dimensional plane that you can draw through the Earth and the sun. So Earth and sun are 2 points in space, and the Earth has a particular orbit around the sun. So if you take that orbital plane, that is our reference. So we still always have to use the sun. The sun is always at one of our focus, right? It is the focus of the ellipse. So you are always considering the sun. This yellow little dot is the sun. But the ascending node is intersection of 2 different orbits. The first orbit is the reference frame, and the second is the plane of this other planet, say Mercury or Mars or whatever. So this is more clear, I think. The second row is the side view. First was the top view. So in the side view, in the first case, it's kind of flat. You see that, right? In the second case, there is some tilt. And in the third case, you see the ellipse drawn and the ascending node. So if the object is moving like this, it's going from southern to northern direction. So this is how you would define the ascending node, right? So So far, what have we defined? We have defined the orbital inclination. Then we've defined the ascending node. You can already start to see that if you have these two things defined, it's actually quite simple to visualize this orbit now. Let's say you had nothing else. I give you no picture, nothing. I just tell you that you have the Earth-Sun orbital plane, and there is this second planet. Okay, it doesn't matter what planet it is, but I give you exact orbital inclination and the exact ascending node, and you should already be be able to kind of picture the orbit. So that is how you would model it as well. And finally, you've got the argument of perihelion. So, okay. So what is the argument of perihelion? I think the top view here is a better approach to it. So now you've defined the inclination. You've defined the point of intersection called the ascending node. But what about the tilt of this entire plane with respect to the focus, right? So this ellipse could have also been pretty much in the same plane. Remember, now I'm talking about the same plane, but then the angle could change. So do you guys see this x-axis? Let's just take the x-axis, right? And let's take this semi-major axis, and let's call it maybe n or whatever, like some normal plane line over here. So the angle made by that semi-major axis and x-axis would be your omega. That is your argument of perihelion. And if it was straight, if they both were aligned, you would have an argument of perihelion equal to 0, right? So how are we exactly defining this? So you can see that it's still flat here. The change of this particular parameter omega will not change the plane. This movement is still happening in the plane. Got it? So the only difference is that this is like, you can think of it as an egg, right? And I roll the egg on a plane. I keep it on my dining table and I just roll the egg as it is lying down on a dining table. Then what would happen? The entire ellipse would simply rotate, right? But the plane on which this egg is still the same. So hopefully that makes a bit of sense. So this is the third missing element. So once you've described this, you've just fully described this orbit of this new planet, right? Whatever it is. So if we rotate the axis of the orbit around the focus, then the rotation angle is the argument of perihelion. This is demonstrated in the diagram below. So as you can see, it can be perfectly flat from the side view, and nothing will change if the argument of perihelion changes. It's just rotating like this or like this, right? So I think videos will be better. I'll just try to send over some links that also try to describe the orbital elements. So these three are important. And finally, you have speed. I'll leave this for you guys to go and read up about it. So there is orbital velocity, mean anomaly, and mean daily motion. So you guys can look that up. I think this is a pretty good diagram. So you've got the node, you've got some orbiting body, first of all. Let's say this is the sun, right? Then you've got semi-major axis and eccentricity that defines the entire orbit. Then you've got the orbital plane, and that is making a particular angle with the ecliptic plane. So this is called ecliptic plane. Those of you who don't know what the ecliptic is, right? It's this plane that is defined by the sun's motion across a particular year, and the earth is moving around the sun, right? So the apparent movement of the sun produces a plane which is at a 23.5-degree tilt to the equator of the earth. So that would be your ecliptic plane, a reference plane, right? So that is nothing but the plane through which the earth is orbiting, the orbital plane of the earth. So this angle is I. We already spoke about what omega is, this omega. And then finally, you've got this other omega, which is nothing but the argument of perihelion. So this is the point of closest approach is nothing but the perihelion distance, right?
I just have a doubt. Can I ask?
Yeah, sure.
So by the diagram, we can actually say orbiting, right? We can define complete orbit
Exactly.
for the year.
Yeah.
So can we calculate velocity? of Earth? Like, can we calculate velocity of Earth moving around the sun? I just came across that we'll generally consider it as circle and we calculate.
Okay, but when you're talking about the velocity, you can actually do that with Kepler's laws, is what I'm guessing. So if you can have the time defined.
Kepler's third law maybe.
Yeah, so if you have the time and the radius of the orbit defined, that already tells you, I think, enough information to calculate the orbital velocity of Earth, and you would still be looking at an ellipse. You don't have to make the circular orbit assumption to be able to calculate velocity.
Okay.
So that can be an exercise. So maybe calculating Earth's orbital velocity is a good exercise. So we can definitely do that. Okay.
Yeah.
Okay. So I think we are kind of clear on orbital elements right now. So this omega is ascending node, right? We spoke about how it is intersecting the orbital plane at a particular point. So this direction is kind of like a reference direction, and it's 0 degrees. You don't have to worry about this. Pisces is like a constellation, and we take that as a reference point in order to define the ascending node. All right. So please come back to this page, revise this. Let me paste it over here. Who was that who just asked me the question? Sorry, I didn't. Was that Manasa, Anjali? Who was that?
Anjali.
Anjali, right? Okay. All right. So all of you can try that little assignment where you're, you can just try to calculate the orbital velocity using Kepler's law. So this is a good tool as well. I think understanding ellipses mathematically can be extremely helpful here. So next thing is, for those of you who are new, this is our Google Classroom page. And we post all our content, our material, assignments, literally all documentation happens over here. And there were a couple of links that I had. Okay, let's use this link today. Is the orbital velocity constant? So it's around 30 kilometers per second for the Earth, and it is not constant because when the Earth is closer to the perihelion, it's going faster, and when it is away from the sun, it is going slower. So what is constant is according to Kepler's second law, which is nothing but the area covered, right? So orbital speed in an ellipse cannot be constant. You can think of it like a sling, right? So when it's going closer to the sun, it's getting slung and it has to go faster. And then when it's away from the sun, it has to go a bit slower. But it will always be covering equal areas and equal amounts of time. That's what remains constant.
Gravity plays a role in orbital velocity, right?
Gravity plays a role?
I guess.
Of course, definitely. So the entire t square is proportional to a cubed. Actually is derived, and that's only a proportionality, right? Can you find the actual equation? That can be the second assignment. So one is to be calculate Earth's velocity. The second could be equation relating T and A. So till now we've only been speaking about, t square is proportional to a cube, but if you guys can go back and actually derive the actual equation where that proportionality comes from, that will give you a lot more understanding. All right, so that definitely has the universal gravitational constant there, and therefore it comes from gravity for sure. So yeah, like I said, it's around 30 kilometers per second. That is the Earth speed, and this is, it varies. So it varies when it's closer to the sun.
Excuse me, can I ask?
Yeah, sure, sure.
I actually got to know that, but after equating, considering the rotation as circular orbit only, they had said that 30 kilometers per second.
Yeah, 30 kilometers per second could be an approximation, but the actual, if you look at the eccentricity of the Earth's orbit, it's extremely small. So because of that, there could be a lot of calculations that do the approximations. Eccentricity of Earth's orbit is pretty much close to 0, right?
Yeah, so if it was a circular motion, then it would be 30 kilometer per second, like constant.
Yeah, it would be constant and it would never change, right? So the reason it is
After
subject
knowing
to
the orbit and everything, why can't we calculate the velocity? Like, at least for an year, can't we calculate?
Yeah, so like we can do one thing. We can do the velocity calculation by assuming it is circular, and therefore you don't have to worry about whether it goes slower or faster, right? Then you can calculate like an average orbital velocity. So 30 kilometer per second is a pretty good approximation for the average orbital velocity. So that could be the first step. How it fluctuates throughout the year would be the next step, right? And that you would have to calculate sort of how close the Earth is to the Sun at the perihelion point, and from that you can calculate the velocity. And you would need that perihelion distance though. But if you're doing a circular assumption of a circular orbit, then no. So let's try with Kepler's law first. We'll do it. We'll take 2-3 days and do it as homework, and then we'll first derive the 30 kilometer per second. Then we'll try to look at the fluctuations in the orbital velocity. So yeah, so like I was saying, this is a good reference point for magnitudes. So those of you who want to have a quick revision of magnitudes, I thought I would cover that today as well. Okay, so maybe you can do the reading. So let me just give you some amount of this thing. So magnitudes is a system for defining brightness of objects, right? And this system came quite a while ago, when people would still not have telescopes, but they were dependent on just naked eye observations of objects. At that particular point of time, there was a limitation to what you can observe, right? For example, the human eye cannot see any object that has a magnitude above 6. And you have to get used to this weird convention in astronomy. So smaller the magnitude is, higher the brightness of the object, right? There's like this weird convention. But yeah, so if it's a negative, it means it's very bright, right? So smaller the value, higher. So the reason this comes is because we use a logarithmic scale, and it has historical reasons, right, why it is opposite that way. So
is it just like for analysis, like it's just for analysis, or it doesn't work for reality? For sun,
no,
like
actually it's a way of defining. You can, for example, you can say, how do we define length in nature, right? We use a meter stick. So that works even in reality. You can say, why are you using a meter stick? Exactly. Why can't you use some other distance? And the way we define a meter is very arbitrary, right? It's like this random distance we chose, and we said this is going to be our unit, right? And it still works. So basically, here we have this random notation where we say 6 is the limit for the human eye, visibility, and then we go negative. We go in the opposite direction. So the greater it is, the fainter an object is. That's just a convention, but the sun would therefore have a MV of minus 26.8. This is apparent magnitude. Usually when you see a lot of negatives, you're usually talking about the sun, especially if you're looking at it and it's like minus 26. That clearly tells you it's apparent magnitude. So the difference of apparent magnitude and absolute magnitude is this, right? Can someone explain? Because all of you, I think, are very familiar with this, so I don't have to go through it again. Who is familiar here? So maybe Anjali, can you tell me the difference between apparent and absolute magnitude?
I don't know, but apparent means what we see. I don't know the other term.
Okay, that's basically the essence of it, but a little bit more detail would be good. So maybe Sampada, are you there? I don't think she's there. How about Prathamesh, are you familiar with the concept of apparent and absolute magnitude? Yeah, those are
Okay,
unmuted.
what?
So is it
Yeah,
like
okay.
absolute magnitude is like if a star is at a distance of 10 parsec, and apparent is the brightness with which it appears to us.
Yeah.
Okay, what I have read is like absolute is that one when okay, apparent is what we see. Like if there are clouds and all that, so we cannot see, right? So absolute is the real one. Matlab, it's not okay. I can't say it clearly. The difference between that is there is no disturbance when there is absolute magnitude, but apparent is clearly what we see. That's all. There are no like clear devices when because I don't know the who introduced it, but he just looked into the sky and he noted down, and that's how apparent one was considered. And absolute one, it was like improved version of apparent magnitude. And for absolute magnitude, everything was considered, like if there are clouds in between and all of that. Basically, that's the reason. And for mathematics, there are like, derivations and all of that.
Okay.
Yeah.
Can we
Um,
simply say apparent is from Earth and absolute is something from standard? Like actually, definition says that it's from standard distance. Distance. So it's something different.
okay. So yeah, we got quite a few definitions there. I think Sampada wanted to say something. Can you unmute and talk?
No, I just wanted to say the same thing. Like, apparent magnitude is measurement from the Earth, and I mean measuring the brightness of the star from Earth, and absolute maybe from a great distance, something in parsecs, light years.
Yeah, 10 parsec.
Okay. So basically, I think Angel, what you were talking about is a slightly different concept, right? So apparent
Yeah,
magnitude.
I was just, it's like history or something.
Okay. Yeah. Got it. So basically, from Earth, whatever observations you're making, and how the star looks to you on a particular night, that is apparent magnitude. But the effects that you spoke about, like atmospheric effect and atmospheric extinctions, those are further corrections that have to be made. Okay. But essentially, by definition, if you look up at some object and you can measure its brightness for you, right, with respect to you, that is apparent. But as you all know, stars are at various different positions, very different distances, right? So one extremely bright star could be extremely far away. So it would seem as if it's the same brightness as a very dim star that is much closer to you, right? So that's the most important thing to consider. So distance plays a huge role in apparent magnitude. So if you take that same distant star, and let's say it is at 200 parsecs, right? What if you could bring it to 10 parsecs? What if you could take every star out there and keep it at 10 parsecs away from you? How bright would it be? Now you've created a generalization. You've created a universal way of defining it, which is not dependent on distance. So that is called absolute magnitude. Because the sun is so close to us, it's literally the brightest thing that is known to us, right? It's extremely bright, minus 26 magnitude. But why does it seem so bright? Only because of distance. In reality, if you put the sun 10 parsecs away, it's actually quite a dim star, and it's just a decent enough main sequence star, right? So this process of kind of equating everything and making sure that you're looking at everything from the same standard point of view, that is called absolute magnitude. So why did we pick 10 parsecs? It's just a convention. Hopefully you all know what a parsec is. Can someone tell me what 1 parsec is equal to?
3.26 light years.
Correct. So 10 parsecs, yeah.
How do you know the distance between Earth and the far away star?
Okay, so that is what we're going to do in the next class. So this is an entire field of astronomy. So distance measurements in astronomy is the most important thing. And as you just said, you understand why, right? If you don't know the distance, the only information you have is apparent magnitude. Yeah, tell me.
One more thing, we are like in federal year or any this one, we are actually saying a distant star, right? So is there any star like that practically using, like in use? If we are changing to another star, then it would be like completely different value, right?
Okay.
So I want to know what is that star we are using for absolute or any federal
Okay.
year.
Got it. So we are not using a star for absolute reference. We are using distance for absolute reference.
Okay.
Okay, so you're taking every star out there and you're saying at this particular distance, how bright would it be? It's like a hypothetical question. It's like you're taking the sun and you're pushing it away to 10 parsec, and then from Earth, you're standing and watching. And then you're like, okay, wait, how bright is it really? So if you put all the stars at that same line of distance, then it's a constant way of looking at it, right? So now distance doesn't come into play over here at all. So
that means the brightest star is like made into like dimmest, and dimmest star is made into a bit brighter. Is that way?
yeah, so depending on the distance, everything comes into a single line, a single distance. So now you know the difference between a really bright star and a really dim star, right? Otherwise, if a really bright star was very far away, you would think it's a dim star. So how do you come to know how bright a star is? You don't know, right? If the dim star was very close to you, you would assume that it's a extremely bright star, but it's actually not a really bright star. It's just close to you. So in astronomy, how do we make these distinctions? We make it by neutralizing this distance factor. We just put all of them, assume that all of them are at 10 parsecs. Then how bright would it be? That is how you define absolute magnitude. But the most important thing here is knowing how far the star is. Otherwise, you cannot make this assumption. Okay. Another thing is luminosity or apparent luminosity follows the law of inverse square of distance, right? For example, the amount of, let's say, brightness of a star from Earth is inversely proportional to r squared. Okay, so you can write something like L is proportional to 1 over r squared. So the farther the star away a star is, then lower the brightness is, right? The closer the star is, higher the brightness. Okay, so that inverse proportionality is there. So using this relationship, we can make judgments about how bright a star really is using absolute magnitude. But this is where we come to the field of distance measurement. So we're going to be going into that. Before that, let's again make sure that we understand some of these things. So you guys can still see my screen, right? So Jupiter at brightest is minus 2.7, right? So these are naked eye limit is 6, right? You can't see anything after this. And Hubble Space Telescope is extremely dim. It's 31, so you definitely can't see it. So table 2 magnitudes and intensity. So now look, let's read this quickly. While you may perceive one star to be only a few times brighter than another, the intensity of these two stars may differ by orders of magnitude. The eye is a logarithmic detector. While the eye is perceiving linear steps in brightness, the light intensity is changing by multiplicative factors. So what they're really trying to say is that the reason we came out with a logarithmic scale, the magnitude system is a logarithmic scale, all right? In the next class, I'll try to have like a nice chart where I can define it better. So we'll go into magnitudes more and distance measurement more. But the reason magnitude scale is logarithmic is because our vision is logarithmic. So when we perceive brightness, if the brightness of something increases 1,000-fold, imagine if even your perception of it would increase 1,000-fold. It can't happen, right? Your eyes would get fried. So the way nature has evolved our vision is to keep it logarithmic. So you see something like a 10-fold increment for a 1,000-fold increase in actual brightness. Okay, so we'll come to what a logarithmic scale might look like and stuff like that. So given the eye is a logarithmic detector and the magnitude system is based on the response of the human eye, it follows that the magnitude system is also a logarithmic scale. In the original magnitude system, a difference of 5 magnitudes corresponded to a factor of roughly 100 in light intensity. Okay, what does this mean? So basically, if I had 1, 2, 3, 4, 5, right? The 5th magnitude star would be 100 times dimmer than the 1st magnitude star. Oh, sorry, the 0th magnitude star. So a difference of 5 magnitudes corresponds to 100 in actual light intensity. So when we speak about intensity, we are talking about actual light emitted. All right. The magnitude system was formalized to assume that a factor of 100 in intensity corresponds exactly to a difference of 5 magnitudes. Okay. So this is kind of the relation you get. What does this mean? So if you take 5 steps, let's think about it like you're climbing a staircase. Okay. Let's imagine that you're climbing from the ground floor to the 1st floor. And I tell you that every time you climb up 5 stairs, your brightness goes down by 100 times. 100 times means current brightness divided by 100. Right? That makes sense. Now, if for 5 steps it is 100 times difference, then what is it for 1 step? It is 100 to the power of 1 by 5. Right? It's multiplicative, so you have to do 1 by 5. So you will realize that the change per step, as you go and climb the staircase, you're climbing 1 step. For that single step, your brightness decreases 2.512. So if a star has a brightness magnitude 0 and another star has a magnitude 1, the difference in relative intensity is 2.51. But if you take a 10 magnitude star, it is 10,000 times dimmer than a 0 magnitude star. 10,000 times. If you see a 15th magnitude star, it is 1 million times dimmer than a 0th magnitude star. Okay, so what a logarithmic scale does is it kind of takes this huge wide scale and it compresses it down into perceivable magnitudes. Okay, so it takes like this 1 to million is a huge scale and it compresses it down to 0 to 15. And that's the power of having these in the logarithmic scale. It's also easier to do calculations this way. So we'll be solving some of these problems. Star A has an apparent visual magnitude of 7 and its light intensity is 100 times dimmer than that of star B. What is the apparent visual magnitude of star B? Okay, I'll give you guys a couple of minutes with this. I posted it on the chat box. Who can tell me the answer first?
$630.
What is the apparent visual magnitude of star B? 6.
No. I calculated the relative intensity, I guess. Right.
Okay. So remember that for every 100 times increase in brightness, magnitude of 5. So 100 times increase in brightness corresponds to magnitude of 5. That means, remember, as you go up, brightness is coming down. If you go from 0 to 5, Bhuvana is saying 2 is the answer. Is that correct? Star A has an apparent magnitude of 7. Light intensity is 100 times dimmer than that of star B. So we already know that B is brighter than A. So if it is brighter than A, what is the apparent visual magnitude of star B? Perfect. So remember that brighter means it has to be a lower magnitude. So Bhuvana got it right. So let's just take a look at this. Sorry, where was I? So yeah, remember that it's just subtraction. All you have to do is subtraction. Light intensity is 100 times dimmer than that of star B. What is the apparent visual magnitude of star B? Okay. So if you guys solve this, I think we can get ready for some brilliant chapters, because there the problems are a bit more, you have to be extremely attentive and you have to be able to solve it on the go. So please get used to, solving problems during the session, right? So we'll be doing that in the future classes. Now this has, okay, let's try this as well. Looks very simple. Don't look at the answers. Okay. What does it say? Star A has a magnitude of 2.5. Intensities. Yeah, this is also easy. Come on, guys, think. You can do it. Think. Remember that you're compressing it, right? 100 times change equals 5 steps in the magnitude scale. 5/7. Okay. Anybody else? Okay, Bhuvana, can you unmute yourself and explain this? If you're here.
Okay.
100 to the power of 1 by 25. I want.
It's 100 power 2 by.
Yeah, can you tell me, Bhuvana?
No, it's 100 power. We should do 4.5 minus 2.5.
Okay, that's just 2, right?
Then we have the magnitude of the difference between them.
Okay. I think she's close. So.
And from the table above, we have Vishal.
Yeah. No, Bhuvana has written 100 to the power of 1 by 25.
Okay,
I think that is close. What is your answer, Vishal? Like, what is your final answer?
Yeah, no, it's 100 power 2 by 5.
2 by 5 is your answer.
6.309. Yeah, 100 power 2 by 5. 6.30957.
Okay. Did you also do the ratio of IA by IB? Or the intensity variation?
No,
but I think you got it. So let's look at this. So 6.3 is what you got, right? Okay, so the difference in magnitudes between the stars is 2.
Yeah, 6.3.
So the intensities must differ by a factor of 2.5 squared. So the shortcut to do this is to, instead of doing 100 to the power of 3 by 5, 2 by 5, each time that I tell you a difference, all you have to remember that is for one step, it is 2.5. And whenever you have to do it for 2 times, you have to square this. Or if you're looking at 3 steps in the magnitude difference, you have to cube it, right? So 2.512 squared would give you 6.31. That's how simple it is. And this already tells you the intensity ratio, not the difference. It's not telling you IA minus IB. It's already telling you IA divided by IB, right? Star A is brighter because its magnitude is smaller than that number. So yeah, IA by IB should be larger than 1. So 6.31 is the correct answer. Okay. So this equation is also easy to understand. You're saying IA by IB equals 2.5 whole to the power of MB minus MA, right? For example, if I'm going from a magnitude 1 to magnitude 5 jump, what intensity ratio am I talking about? Well, 1 to 5, so 5 minus 1 is 4. So that's just MB minus MA.
I just have it out. Why are we using 2.5? That one, I think I just missed out.
Okay, so basically, you have a simple rule to begin with. For every 5 steps you take, it is 100 times increase or decrease. For example, if you go from 5 to 0, it is 100 times increase. Okay. Now that means that for every step, what is the increase? That's the question. If I take 5 steps, my increase is 100 times. If I take 1 step, what is my increase? Because it is multiplicative, you can't just do divide. You have to do 100 to the power of 1 by 5. Okay. So you have 5 steps. So how much is 1 step worth, right? Or how much intensity is 1 step equivalent to? So you have to do 100 to the power of 1 by 5, and that gives you 2.512. So this is the standard number for every step of difference in the magnitude. For example, if I go from 0 to 1, the intensity increase is 2.5 times. Okay. This is 2.5 squared, 2.5 cubed, 2.5 to the power of 4. Got it? So whatever magnitude difference you have on the left side that you're talking about, you just have to take 2.5 to the power of that. So 10 power 6 is close to 2.51 to the power of 15. So that's why you get a million over here. All right. So it's logarithmic. Cool. So this is kind of the equation you should keep in mind. We will continue reading the rest of this thing in the next class, but it would be extremely helpful if you guys can go through it yourself. Because to just give you a clue, in the first mini project that some of you are going to do, this is the most important equation you're going to be using. D is equals to 10 power. So this actually relates distance to magnitudes. All right. So to be able to get here, D is equal to 10 to the power 0.2 into M minus capital M plus 5. So what are the equations you have to go through to get here, right? This is the most important one. And yeah, so figure it out on your own. Try to derive it on paper, otherwise you'll never understand. It's slightly tricky, but it's also extremely simple. Like you're looking at a scale and you're trying to figure out how these numbers can be correlated. And you bring in this concept of absolute magnitude, capital M here, right? And how that is related to small m. That also you can see over here. Okay. So please go through this. I think we can end here. I don't want to take too much of your time today. But this is a classroom is something all of you should join. For those of you who are working on data sets, Abhilash has posted the car sales one on the classroom. So just play with it. This is not related to astronomy. It's an extremely simple data set. Even if you know only Excel, you can still do some exploratory data analysis on it, right? So this is how it looks. You have quite a few columns over here. All you have to do is, if you already know Pandas, great. If you know another programming language, do it. But if you know just Excel, try to plot this and this. Try to find the mean of this. Try to find the median of this, right? So that's exploratory data analysis. See if that you can find any obvious correlations, right? You don't have to do like any other regression modeling or whatever. You just have to do some amount of correlation and get familiar with how you can handle data sets. So that was the homework from data analytics. Please be interactive in his class as well. Like he's putting in a lot of work for this course. So make sure you finish the assignments before you show up for the next class.
Can you share the classroom code for this?
Yeah, I'm sharing. I'll send it to you guys on Telegram. Okay. So yeah, so we'll end here. Just to give you a visit of how brilliant looks like. I'll show you that as well. So we are going to be using. There are a couple of things we missed out. Even the other people, older people, they've not done it. So for example, I think matter and gravity we should become. So these will seem like it's easy, but these are hardcore problems you need to solve on paper, and we're going to be doing this together. So it looks like this. We just have to solve numericals, and it gives us a proper foundation. And so next class, hopefully, if you guys can do the reading of magnitudes, then we'll be able to finish HR diagram and maybe even gravity. So we'll do gravity and HR diagram in the next class. So this goes all the way to distance measurements, which is extremely important. Yeah, we can do this as well, apparent magnitudes. Then there is stellar evolution. So we'll go to stellar evolution a bit later. So Sampada and Ankita, we didn't do exoplanets together. So we're going to be doing worlds beyond Earth as well. And in maybe 2 weeks, we'll come here. So I'll just keep you guys updated. You can join whichever sessions that you were not there for before. Even otherwise, the classes are like revision for you. So you can join for sure. Yeah, we'll end here. Sitara, can you send me the video of lecture 2? You're talking about data analytics, right?
Yeah.